Okay, so today we're going to take a look at a little bit of wave mechanics. So the first question that we're going to deal with is taking a look at a speaker that's generating a tone, and that tone is, let's go with 750 hertz. And that tone, this is measured in hertz, which means that it is my frequency. And let's see, this shouldn't take but a moment to set up. 750. Let's see what that actually sounds like. Here we go. Delightful. But that's what the sound actually sounds like, 750 hertz. And I'm hearing it here in the classroom in air. We're going to assume that, normally we assume that the speed of sound in air is about 340 meters per second. It will fluctuate some depending on the temperature. Usually 340 is kind of the quoted number. The measurements I've been getting in the classroom here have been a bit closer to 320 meters per second. So for this one, and to make certain that the numbers are a little bit different, we're actually going to go ahead and use that. So I'm going to go with empirically found a velocity of 320 meters per second. And my question is what the wavelength of that particular sound wave is. Okay, well, I will use my equation that the velocity is equal to our frequency times wavelength, and I can basically just plug things in. I know that 320 meters per second equals my frequency, which is 750 hertz. Remember, hertz is the same thing as 1 over seconds. It's also called inverse seconds. Times our wavelength. All I need to do is solve for wavelength, so I'm going to divide both sides by 750 hertz. And I find that my wavelength is 320 divided by 750. This gives me 0.426, technically repeating, but let's stick with 3 significant figures. So I would round to 0.427. What are my units? Well, I've been using SI on everything. This is a length, so it should come out in meters. So we're just shy of 43 centimeters. So let's double check on those units. I have meters divided by second, and I'm going to divide that by hertz, which is 1 over seconds. So I've got this weird compound fraction thing. What I'm going to do is I'm going to multiply the top and bottom by the same thing. I'm going to multiply it by seconds over 1 so that I can get this to cancel out, and I get the weird denominator of the denominator gone. Okay? So I can evaluate this, but these seconds cancel out, and I'm left with, indeed, meters over 1. My answer for this, the wavelength of that particular wave that we heard just a moment ago, is actually just shy of 43 centimeters, at least in the classroom here. Delightful. Okay, here is an app that I use that actually keeps track of frequencies. And so this is in the classroom here. You can see as I speak, it's actually doing what's called an FFT of my voice. And so you can see when I speak or make noise, it crops up. Ignore the spike at 9.3 kilohertz. I think that's actually something that it always shows up pretty much. The first thing we're going to do is we're going to check the frequency generator that I used earlier with my phone. So it is currently set to 750 hertz. So let's hear. We had a spike there at about 753. So that may also tell me that either one of these could be slightly off. My equipment may not be as accurate as I'd like. But this is a good way that we can actually get some measurements.